Alright, suppose A, B, C, and D are sets. Prove that A times B union C is equal to A times B union A times C. Alright, let's draw a picture of this and see why it might be true. So let's represent A by just a line segment like that, and B by another line segment in a different direction. So that's B. And then C by another line segment. I'm going to be doing B union C, so maybe I'll make them overlap a little bit. Okay, so this whole vertical line segment is B union C. And for taking A times B union C, then we're going to get sort of this solid rectangle, kind of like this. Okay, colored in on the inside as well. So that is A cross B union C. Now that's the same as the right side because, well, what's A times B? That would be just this squarish looking object here. And then A times C would be everything above this line, right? This whole part. And so if we take the union of those two sort of almost squares, then we get the whole big rectangle again. Same thing as we got for the left side. Alright, so let's prove this. We've got our given or our goal. And to prove that two sets are equal, we would like to prove that for all P, which I have not written here. For all P, P is in the left side if and only if P is in the right side. Okay. Now I didn't write that because we're about to drop it anyway, right? Let P be arbitrary. It goes away. And now to prove the biconditional, we prove two conditional statements. Left implies right, and right implies left. Good. Now, actually, we can even back up a step and just let's go back to the biconditional. I'm going to prove this statement in three different ways. Okay, so the first couple ways are just basically showing that P being in this first set is equivalent to P being in the second set. Okay, and so let's give that a shot. All right, so to start off the proof, we do drop our for all. We let P be arbitrary. And then we're going to show that P is in here if and only if P is in here. And alright, so we have P in the left side if and only if. Well, let's just write out the definition of that. There exists a first coordinate x and a second coordinate y such that P equals xy with the first coordinate in A and the second coordinate in B union C. And then we're just going to keep rewriting that. And the first step is that y being in the union means y is in B or y is in C. And now I have this statement and this one, and so I can distribute that and to get x in A and x in B, or x in A and x in C. And then, well, if x is in A and y is in B, then that means that the point xy is in the Cartesian product A times B. And similarly over here I get xy is in A times C with an or in the middle. And then for xy to be in here or in there means that it's in the union of those two sets. Okay. So overall I have an x and a y such that P equals xy and that point xy is in here. Well, that means that that P is in that set, right? If it can be written that way, and if that's in here, then P has to be in there. And all of those steps are reversible, so they're all if and only ifs, and so we're done. We've proved that P is in here if and only if P is in there. Now it's a little bit annoying having all of these there exists here, and there's actually a way to sort of be a tiny bit less rigorous maybe, but to write this in a simpler way that's easy to understand. So we start off the same way, let P be arbitrary. Actually I wouldn't want to say P there, right? I'm going to say xy, okay? Because instead of using P and then saying that there exists a first and a second coordinate such that it can be written as an ordered pair like that, I'm just going to sort of show that an ordered pair is in the left side if and only if it's in the right side. Okay. Sort of using the fact that if something's going to be in here, then it's definitely going to be an ordered pair, right? This is a Cartesian product, and so we can go ahead and write it that way and not worry about all these quantifiers. All right. So we just have that xy is in the left side if and only if first coordinates in A, second coordinates in B union C. Split that up into a disjunction. Distribute the x in A just like we did above. and then change these two statements into the facts that x, y is in these two Cartesian products, and then the OR becomes a union again. So basically, what I've written down here is sort of a subset of what's up here, right? Just a simplification that we've made by not talking about this P. All right, well, you might wonder, can we do this proof using the techniques from the previous chapter? And we can, and let's do it for some good practice, although I think I kind of like this second proof best. Okay. So let's look back at our givens and goals. As we mentioned, we could break that biconditional up into two conditionals and take them one at a time. So for this direction, we can do direct proof and bring our antecedent over as a new given. And then we use the definition of Cartesian product. Right? If P is in here, then we have an x and a y such that P equals xy, with x in the first set A and y in the second set B and C. And over here, P being in the union means that P is in the first thing or P is in the second thing. And then, all right, well, we need to do a couple existential instantiations here, so we get an x naught and a y naught such that this statement is true with those plugged in for x and y. I'd rather avoid all those naughts on the x and the y, so let's just sort of remember that's the technique we're using, but we're going to abbreviate a little bit here. And so we would get this big statement, and that's just three statements connected by ands, and so we can write them on separate lines. So we have those three givens, the same goal, and our third given here is, well, it's a union, which is really an OR statement, right? Y is in B or Y is in C, so we can break that into two cases. Bring down our other givens, and let's see, in the first case we have Y in B and X in A, and so we're probably going to want to prove that P is in A times B, right? And similarly in the second case we'll do P is in A times C, our other option. And okay, so we got it. In case case 1, P is xy, x is in A, y is in B. That's exactly the definition of P in A times B. And in case 2, we have P in A times C. All right, so let's try to write down that proof. We start off just as before by letting P be arbitrary, and then we're going to show that this if and only if that. And now we do the forwards direction. So we're going to prove this one, and we start off with direct proof. So we suppose that P is in here, and then this gives us our new goal. And then after that, we use the definition, and then we said, well, there must exist an x and a y such that these guys are true, right? And so let's write that down. We know, oops, wrong place. We know that there exists some x in A and y in B union C such that P equals the ordered pair xy. Okay, good. And well, from there we decided to break up this union into a disjunction and get a couple cases from that. Right. So let's begin writing down those cases. Case 1. We're going to suppose that y is in B. And all right, well, we have x is in A and y is in B, and P is xy. So we can say then it follows that P is in A times B, which was our goal in that case. And then for the other case, we're going to do something similar. Case 2, suppose y is in C. Then in this case, P is in A times C. Okay. And in either case, P is in this union, right? Okay, finally the other direction, which we didn't work out over here, but it's quite similar. Suppose we have P in the right side. We're going to show that P is in the left side. So if P is in here, then either case 1, P is in A times B, or case 2, P is in A times C. it's an A times B, then we have an X and an A and a Y and a B such that P looks like that. And similarly in case 2. And in either case, Y is in B or Y is in C, right? So in either case, Y is in B union C. And in both cases, we also have X in A, and so we have that the point P is in A times B union C. And we're done.